Yeah, hello everyone. This is the NPTEL course Functional Analysis, and this is the problem solving session where I'll explain you some sample problems from the assignments that will help you to understand the concept better and maybe help you to solve other problems by your own. We are in week 10 and I am PMRFTA. Come on. Okay, okay, so let's get started. We are on week 10th, assignment 10th, question number 1. Okay, let okay, let me check once. Yeah. So let H be a Hilbert space. A subset K is called a cone with vertex at the origin if 0 is there in the cone, and for every element x in K and every real number alpha non-negative, alpha x should be in K. Okay, so K should be closed under non-negative scalar multiplication and 0 should be there. So that's how we define a cone with vertex at origin. Okay. Now let K be a subset of H be a closed convex cone in with vertex at the origin. Okay, so we have K as a closed convex cone vertex at origin. Yeah. What that means? K is closed under the norm by Hilbert space. Convex means for all x, y in K and alpha 0 to 1, we have alpha x plus 1 minus alpha y belongs to K. This is the definition of convexity. Definition of cone is there in the question itself. Okay, so we have this setup, and for each x belongs to H. Okay, PKX is the the point closest to x in K. Okay, this is kind of projection of x to K. Yeah, similar to projection. So which of the following statements are true? First one is if x and y in the cone and if alpha and beta are non-negative real numbers, then we have alpha x plus beta y in the cone. Okay, so without the A, what do you have x comma y in the cone and alpha comma beta greater or equal 0. So from the definition of cone, we know alpha x comma beta y both belongs to K. Yeah, and from the convexity of the cone, if I put alpha equals to half, what I get is x by 2. I mean alpha x by 2 plus 1 minus half, which is again half beta y. I mean, in place of x and y, I am substituting alpha x and beta y because both are again an element of K. This is in the cone. And what is it? This is alpha x plus beta y by 2. This is in the cone. And now again the property of cone that's closed under scalar multiplication non-negative. I'll multiply it by 2. Implies 2 times belongs to the cone. So this was pretty straightforward. Now if x is in H, then pkx satisfies this condition. Okay. Okay, let's see. Hmm. Okay, what we want is inner product of x with pkx equals to norm pkx square. Okay, yeah. First thing is, see, if I give you a geometric intuition, Suppose this is the point pkx and this is the point x. Yeah. So this vector is x minus pkx. Okay. So now suppose you consider any point y in the cone, and this vector is now y minus pkx. Correct? Okay. So what does it mean if geometrically, because we are in a real inner product space, so I can assume this inner product of x minus pkx, which is this line here, with the inner product of y minus pkx, which is this line here. If this inner product is greater than 0, yeah, that means the angle between these two lines is acute. Yeah. If the angle is acute, then you can see this vector. This distance is smaller than this distance, right? If the angle is acute. So if this happens, then that implies what do you say, y is closer to x than pkx. But this is not true because we know pkx is the closest point in k, closer to x. But this is a contradiction. Hence, what we get is inner product of x minus pkx with y minus pkx has to be less equal 0 for all uh, okay, for all y belongs to k. This should happen. Okay, now what? Now in place of y, because pkx is in the cone, and from a what I get is y plus pkx is again in the cone. That means if I put instead of y plus pkx, I'll get inner product of x minus pkx with y to be less equal 0 for all y belongs to k. Yeah, okay, this works. Now, I mean, I'll just change the values of y and maybe let's see what I'll get. If we put now y equals to pkx, this will imply inner product of x with pkx minus inner product of pkx with pkx, which is norm pkx squared less equal 0, which implies is less equal norm pkx squared. Okay, and okay, let's see if we can use Cauchy somehow. What we know is inner product of x with pkx has to be less equal norm x into norm pkx. But anyways, norm x will be less equal norm pkx because norm x is distance of x from 0, with 0 is in the cone, but we know the shortest distance is norm pkx. Oh no, no, there then it will be norm x minus pkx. Yeah, no, this doesn't work. Cauchy doesn't work. Okay, so this one side we have. Okay, let's see if we put y equals to minus pkx, what happens? This implies inner product of x with okay, minus pkx minus, no, not minus, here it will be norm pkx squared. Again, it is less equal 0. That means, yeah, that means norm of pkx squared is less equal inner product of x with pkx. Hmm. I mean, we are not putting y equal to minus x because minus pkx, we don't know if it's there in the cone, but in fact, we are putting here y equals to 0 because 0 is in the cone, right? And when we put y equal to 0 here, we get the same. So, kind of, I'm putting y equal to minus pkx, but that's understood. Yeah. Okay, I'll just write it here. It's to 0 in star. This equation is star. Then pkx square is okay. So then equation 1, 2 implies inner product of x with pkx is same as norm pkx square. So we got what we wanted. So option 2 is right. Okay. it's working. Okay, so now option 3. Okay, no space. Okay, so option 3 says if we have a Z in K with this property, then Z is the projection. Okay, let's see. If Z belongs to K such that inner product of X minus PKX with Z is less equal 0. Yeah, is it what this is? No, sorry, inner product of X minus Z with Y less equal 0 makes Z Z square. Okay. Inner product of X with Z is equal to norm Z square. Ah, this is exact same properties of PKX. We want to show that, I mean, the claim is Z equals to PKX. That is, okay, that means what? The distance of X with Z is less equal distance of X with Y for all Y in K. Yeah, this is what it means. Z is the closest point to X in K. Okay, let's see how it goes. Hmm. Yeah, I mean, intuitionally, it's again the same. If Z is here, X is here, this is X minus Z. And if you take any point Y, what we are getting is uh, X minus Z with Y there. See. Okay, then this Y minus at this point is again in the cone. Yeah, so this came as a right angle. Okay, okay, less equal 0 means it's obtuse angle here. Y minus Z. So this is greater less equal 0 means this is an obtuse angle. So we can see that this has to be away from X than Z. Yeah, you know. So intuitionally it is this, but let's see how we prove it rigorously. Okay. Okay, so let's see how can write X minus Z. X minus okay, we'll start with X minus Y maybe. X minus Y equals to X minus Z plus Z minus Y. Let's see. Or we can write as maybe X minus Z minus Y minus Z, which is greater or equal norm X minus Z. Okay, let's go with squares. And this is inner product of, okay, then we know this thing directly. X minus Z squared plus Y minus Z squared minus 2 times inner product of X minus Z with Y minus Z. Yeah, because this is the real inner product space. In the question we haven't given any description, that means we can assume it's a real inner product space. That's written in the, the first paragraph. Okay, now what do we know about this thing? Okay, so this is norm X minus Z squared plus norm Y minus Z squared minus 2 times inner product of X minus Z with Y minus inner product of X minus Z with, instead of that I'll just write inner product of X, oh no, okay, minus Z with Y minus inner product of X with Z, okay, X with Z and plus, okay, what is the problem? Plus inner product of X minus Z with minus Z. This is this is the same. Then we have X minus, we have 2 times the product of x minus z with y, which is positive now because yeah. But then here I have minus 2 times, this minus gets out, then it becomes plus 2. Then product of x with z plus hmm, it's some problem. X minus z plus z in y. Okay, so if it's okay, let's see, inner product of x with z, then minus goes out, minus minus plus 2. Inner product of minus z with minus z, which is plus norm z. Oh, then minus will come out. Okay, yeah. Then this minus 2 times norm z squared. Ah, okay. But now this guy is again norm z squared, yeah? From the assumption we know from the question. X with z inner product is norm z squared. That's Q1. Yeah. So this whole term becomes 0. What do we have here? Norm x minus y squared is equals to this quantity. So this is some non-negative quantity, and we know this is less equal 0. So minus of this will be greater equal 0. So this whole quantity is greater equal norm x minus z squared. Yeah. So for any y in cone, what do we get? Norm x minus y squared is greater equal norm x minus z squared. That means we are done. Z is the closest point to x in K. Yeah. Cool. Okay, so question number 1 is done. I hope it's clear. Then question number 2. Okay, T from L2 to L2 given as the sequence Tx equals to xi by I. Okay, which of the following are true? Hmm. So let's see about the injectiveness first. Let's assume Tx equals to 0. Then what do we get? X at I upon I equals to 0 for all I. This will imply xi equals to 0. It means x is 0. It means t is 1 1. So injectiveness was quick. Let's see about the surjectiveness and closedness. Okay. What can we say about the surjectiveness? Is it surjective? See, for surjectiveness, what we want is every element in L2 needs to have a pre-image. Yeah. But the element y given as 1 by 2 square, 1 by 3 square, simply like y at I equals to 1 by I square sequence. This belongs to L2. Yeah. Okay, let's see. But okay, if I take the pre-image, it's 1 by n, that is again in L2. Okay, but if we take y as this 1 by 2, 1 by 3, yeah, 1 by n simply. This again, this is also in L2, but what is its pre-image? But if Tx equals to y, then x at I upon I equals to yi, which is 1 by I. That means x at I has to be 1 for all I. But then x doesn't belong to L2. In fact, x is divergent. X is constant one sequence, which the sum which is not there in LP for every p1 to infinity strictly less than infinity. Yeah, so T is not surjective. That's clear. Is the range of T closed? That's the question. Well, what we will use here is any operator on Hilbert space. We know null space of T is equals to range space of T star perp. Yeah, okay, this we know. But also that implies null space of T perp is range space of T star closure. Here, what is T star? Let's see. Inner product of Tx with y is summation xi upon I into yi, which is okay. We have a real inner product space, so L2 maybe not mentioned, so we can assume real. So it's summation xi upon xi into yi by I. I can write it like this, which is just inner product of x with ty. That means T is same as T star. Hence, null space of T per will be same as range space of T closure. But null T is injective. That means null space of T is singleton 0. That means range space of T closure is the whole Hilbert space. So if range space of T is closed, then T is surjective. But we have just shown that T is not surjective. It doesn't have a pre-image for the sequence 1 by n. So we are through. Oh, sorry. Range space is not closed. Okay. Define T. Okay, yeah, this is done. So let's see if the recording is going on. Yeah, it's working. Mhm. Let AI be a sequence of real numbers such that for every x in L2, the series summation alpha xi convergent. Which of the following statements are true? Okay, alpha belongs to L1. Hmm. Okay, so third A option. If we take x to be 1 by n and belongs to natural number, notice summation AI I mean not x, this alpha sequence, alpha I. Then summation uh, alpha xi equals to summation xi by I and the modulus is less equal, I know norm x2 norm into norm of 1 by squared. Yeah, I mean summation 1 by squared is to 1 by 2. But this is in L2, this is in L2, so this is finite. That means summation xi by I going from 1 to infinity is convergent for all xi belong to L2, but alpha doesn't belongs to L1. So first option is wrong. Let's go with the second. Alpha belongs to L2. Is it true? Okay, let's see. Okay. We want if we want to check if alpha is square summable. Okay, so let's go with sequence of partial sums maybe. I'll define maybe an operator Tn, okay, from L2 to L2 given as if Tn of x equals to alpha 1 x1, alpha 2 x2, alpha n xn, and then 0 afterwards. Like same sequence, I mean summation alpha xi, but for finite terms. Yeah, I mean not summation, just alpha xi, but for finite values n. So this Tn is an operator, this is a continuous operator. And one can check that norm Tn, yeah, is basically less equal summation modulus of alpha I squared raised to 1 by 2, I going from 1 to n. Yeah, if you can check that one easily. Okay, that follows from Cauchy sorts. Yeah, because now because of the finitely many terms, this is again in L2, so just product of two elements. I mean, the Cauchy sorts will give you this thing, and this is not just less equal. If you take particularly the sequence xi equals to alpha I, I mean x to be equals to alpha 1, alpha 2, up to alpha n, then 0, then you get norm of t and x is this quantity. That means, okay, I mean this quantity into norm x, which is again this quantity, so squared. So norm Tn will get as this exact same quantity, summation mod alpha I squared whole raised to 1 by 2, I going from 1 to n. This is norm Tn, yeah, okay. But now what we know is for any x belongs to L2, Tnx equals to, okay, so what is Tnx? Alpha 1 x1, alpha 2 x2, alpha n xn. Hmm. Yeah, yeah, okay. We know that the series converges, right? Summation alpha xi, the option. Yeah, if the summation alpha xi series converges, yeah, then I know this Tnx converges. Yeah, but this converges pointwise Tnx and it's bounded because we know norm Tn is this. So by Banach-Steinhaus, what I know is this sequence of operators is uniformly bounded. That means there exists an M positive such that norm of Tn is less equal M for all n belongs to natural number. Yeah. But what is norm Tn? Norm Tn is the sequence of partial sum of the series, summation modulus of alpha I squared I going from 1 to n. So 1 by 2 is less equal M for all n belongs to natural numbers. This is a sequence of partial sum of non-negative terms. That means the series is convergent. This implies this sequence alpha I belongs to L2. This is what we wanted. Okay. Okay. So this alpha I is in L2. Okay. So let's see the third option, which asks whether alpha n by n converges to 0. Okay. But from the second option, we know that alpha n belongs to L2. And now if we just consider alpha I by I, we know this is less equal summation mod alpha I squared raised to 1 by 2 into summation 1 by I squared raised to 1 by 2. But this is also finite, this is also finite, hence this is finite. Which implies the series converges, hence the nth term will go to 0. So alpha I by I goes to 0. Okay. So option C is also true. Let's move to the next one. Question number 4. Let's see. Question number 4 asks if alpha I be a bounded sequence of real numbers and A is the operator defined as earlier. Ax is equals to alpha 1 x1, alpha 2 x2, and so on. Which of the following statements are true? A is bounded, A is invertible if and only if modulus of alpha is positive. Okay. Okay, let's see. Okay, so now if alpha is bounded, what is norm AX? Yeah. Norm AX squared, maybe it is summation modulus of alpha I xi squared from 1 to infinity, which is less equal mod alpha I, because I'll assume let modulus of alpha I is less equal m for all I belongs to natural number. Since alpha is a bounded sequence, there exists an m. This is less equal m times summation modulus of xi squared, which is finite, or I mean, which is just m times norm x squared. Yeah, okay, so I think we don't have to write the 2 here because we are in L2 space, so that's clear. That means A is bounded. Okay. Now A is bounded in A is invertible if and only if infimum alpha is positive. Okay, so let A be invertible. Okay, that means inverse is also continuous, which implies A inverse of y is less equal some constant beta times norm of y for all y, I mean, there exists beta positive, so that this happens for all y belongs to range of A, yeah, which is again L2 because we are in L2 space, right? Yeah, and it's on to. But this is same as saying norm of A inverse of y is we can call x is less equal beta times norm of y is just Ax. That is norm of Ax greater or equal, okay, I'll just call now this maybe beta dash, which is 1 by beta times norm x for all x belongs to L2. Okay, so this gives you that straight away. Uh, okay, what you can say now? This is happening for all x belongs to L2. So if we take x as maybe standard vectors EIs, then AEI is modulus of alpha I, which is greater or equal beta times norm x is 1, which is strictly positive. So it implies mod alpha is strictly positive for all I. That means infimum of mod alpha I is again strictly positive. Yeah? So this one sided is okay. This follows. Okay, so let's see the other one. So now converse. Suppose infimum of modulus of alpha I is positive. We want to prove that the operator A defined above is invertible. Yeah? So okay, let's see if it's 1 1 and on 2. If it's 1 1 and on 2, then we are done. Yeah, I mean it is enough to show that A is injective, A is bijective. Why? Because of bounded inverse theorem. Once we show it's bounded, but once we show it's bijective, its inverse will be automatically continuous by bounded inverse theorem because we are in the Hilbert spaces, which are Banach spaces essentially. Okay, so task is to show it's bijective. So let Ax is 0 for okay. That means alpha I xi has to be 0 for all I. Yeah, but that means like because if x is but okay, yeah, I mean if infimum of mod alpha is strictly positive, that means each mod alpha is strictly positive for all I. Yeah, but this implies then alpha I xi equals to 0 implies xi has to be 0 for all I. It means x is 0. Yeah, so this goes. It implies A is injective. Now let y belongs to L2, any element in L2. I want to find a pre-image of y. Yeah. So I can write y as maybe y1, y2, and so on. So define x as uh, y1 by alpha 1, y2 by alpha 2, and so on. So question is x belongs to L2? So let's see. Summation modulus of xi squared I going from 1 to n is summation modulus of yi upon modulus of alpha I 1 to n. But now since modulus of alpha I is strictly greater or equal beta or strictly positive, this beta is the infimum of all alpha mod alpha I. That means this quantity here is less equal 1 by beta summation mod yi squared I going from 1 to n. This is less equal 1 by beta now y squared. That means summation mod xi squared converges finite, hence x belongs to L2. So we have the pre-image for every y as this x. That is what we get is ax is y, which implies A is surjective. Injective, surjective means bijective, and by bounded inverse theorems, its inverse is also continuous. Hence, we know that A is A is invertible if and only if infimum of model phi is positive. For the third option, it's easy to observe that A star is same as A, so there's no difference in option B and option A essentially. Okay, I hope it's clear. Okay, let's see. Yeah, it's working. Yeah, because sometimes it just stops working, so I have to check again and again. Otherwise, I'll just keep on doing the session and there's no recording. Okay, so let's move on to question number 5th. Okay, which of the following statements are true? Let L not denote the space of the subspace of odd functions and LE denote the subspace of even functions in L2, then okay, this is just straightforward. Well, first of all, we have to show the intersection is, I mean, just singleton 0. Let L not intersection L, which implies what? F belongs to L naught. So F at minus x is same as F at x, but also F at minus x is same as minus of F of fx because F is also in LE. Yeah? That means F at x equals to 0 for all x belongs to whatever domain it is, minus pi pi. Yeah, that means L naught intersection LE is just singleton 0 function. And now for any f belongs to L2 minus pi pi, you take f can be written as maybe, okay, this fx can be written as fx plus f at minus x by 2 plus fx minus f at minus x by 2. Okay, let's see, is this odd even function? F at minus x, yeah, this is an even function, this is an odd function. Yeah. So you can write every function as the sum of an even and odd function and their intersection is empty, so this is the direct sum. Okay, yeah, this is clear. Now let H be a Hilbert space and A is self-adjoint. Can we write Hilbert space as null space of A, direction and range space of A, where null space of A and range space of A denote the null space and range of A respectively? Yeah, see, this need not be true always, because if suppose A is injective, okay, let's see, if A is injective, then what we know is, because it's self-adjoint, its closure will be the whole space. Yeah, injective and range of A is not closed, then we know that range space of A need not be equals to H Hilbert space. Yeah, so and the second option may not be true. I think we have seen the similar example just now. Where are you seeing it? Yeah, yeah, here. Yeah. In this example, our T was from L2 to L2. Yeah. T was injective, so we cannot write L2 as null space of T. Direct some range space of T if we write, because null space of T is singleton 0. And if this you write range space of T, then range space of T will be whole L2. Yeah, this will equal, that means that T is surjective, but T was not surjective here, so this is wrong. Yeah. So I think this is clear. So this second need not be true, but the third is true. What third is says is HB Hilbert space A belongs to LHB self-adjoint, then we can write Hilbert space as direct sum decomposition of null space and range space. Okay, because see, first of all, we can always write H as null space of A, direct sum null space of A per. Yeah, but what we know is null space of A is range space of A star per. That means null space of A per is range space of A star closure. But if A is same as A star, we have this thing. And hence it follows. That's all. That was there in the option. So option C of the fifth one is correct. Okay, let's go with the question number 6. Just a minute. Okay, let's see. Question number 6. H be a Hilbert space and let x1 through xn be a collection of vectors in H. A is the matrix defined like this. Okay, it's the matrix A diagonalizable. Okay, let's see. How is A defined? Each entry is x1 with x1 inner product, then inner product of x2 with x1. I hope it's correct. X1 2 with x2 with x1. Yeah. Like this, inner product of xn with x1. It goes like inner product of x1 with xn, an1 entry. Yeah. Okay, this is inner product of x2 with xn until inner product of xn with xn. So this is the matrix A. So this is the matrix A diagonalizable. So we know by spectral theorem, every normal matrix is diagonalizable. Yeah. Normal means A star has to be equals to A star, A star A. This is the condition for normal matrix. So let's say this satisfies here. What is the ijth entry of A star? This is summation I kth entry of A times kjth entry of A star k going from 1 to n. So this is what is A I k? I kth entry of J. This is xk with xi. Then A star's kjth entry is the conjugate of jkth entry of A, which is inner product of xk with xj bar. Yeah, but this is just xk with xi times xj with xk. That's all we know. Now let's see what is the ijth entry of A star A. This is summation again A star's I kth entry then eighth kj entry, which is summation. Okay, A star's ikth entry is conjugate of k ith entry of A, which is inner product of xi with xk. I hope it's correct. This is just A ki entry bar, and by the definition, A ki is inner product of xi with xk. Yeah, I'm correct. Yes. Xi with xk bar. Yeah, and then xkj, akj, which is inner product of xj with xk. Yeah, so this is conjugate of xi xk is xk xi. So these two are same. That means A star equals to A star A. That means A is normal. That means A is diagonal. Okay, this solves the first entry, first option. Okay, let's see if A is invertible. For A invertible, that's just very far-fetched. I mean, there is no conditions on xi directly, so we cannot say anything about A. Like for example, if I just assume one of the vectors as xi is 0 and all other vectors are also normal, then the matrix is just a diagonal matrix with one entry 0, so that won't be an invertible matrix. Yeah. So B option is wrong, but we'll prove maybe the condition on when matrix is invertible. Condition is A is invertible if and only xi is linearly independent. Yeah, this is what we want. So let's see how to prove. Let A be invertible, or I mean, invertible means what? Here in finite dimensional space, even if we prove it's injective, we are done. So what if let Ax equals to 0? This happens implies Ax, right? Ax is summation xi aij, yeah, ith row x column of x. Okay, not xi, then xj aij, j going from 1 to n. Okay, right? This has to be 0 for all I, yeah, for each row. Yeah. Okay, what this say? This means, I mean, okay, I should not call it here xj. Already we already have xj. Set a z is 0. This is zj. That means summation in zj times inner product of aij is xj with xi is 0 for all j going from 1 to n for all I, which implies inner product of summation zj with xj 1 to n with xi is 0 for all I. That means this element here, if I call it y belongs to the perp. Mhm. Okay, so okay, first of all, what are we assuming here? Okay, we are assuming first that the set xi is linearly independent. Okay, okay. And yeah, and already y belongs to okay. If the set xi is linearly independent, then this is the basis of Rn, and y also belongs to Rn, hence y has to be 0, yeah, because it's perp with every element in the basis. That means summation zj xj is 0, but xi is linearly independent. That means zj equals to 0 for all j, implies z is 0. Yeah, this is okay. So az equals to 0 implies z equals to 0. We got that means a is invertible. Okay, so one side we have done. Yeah, I mean now I think we can uh, go back. Yeah, in the same methods like okay. So if summation zj aij is 0, I mean if summation if this is 0, okay, I'll just write. What we proved is if the set of vectors x1 x2 up to xn is linearly independent, then A is invertible. This we have proved. Now conversely, suppose A is invertible and consider summation zj xj to be 0, j going from 1 to n. Just the linear combination of these xj's is 0. I want to show that zj has to be 0 for every j. This means inner product of summation zj xj with xi is 0 for all I. This means summation zj times inner product of xj with xi is 0. That is summation zj times a ij equals to 0. That means az is 0. But because a is invertible, this implies z is 0. That implies zj is 0. Yeah, so like the exact same argument, just traced back. So it follows a is invertible if and only if x's are linearly independent. Okay. So now this is going to be used in the option C. In option C, what we want is there exists an epsilon positive. If xi through xn are linearly independent, then for every y in the epsilon neighborhood of x, the set yi is also linearly independent. That's what we want to show. Okay. The first thing is if we define the matrices, yeah, I mean the matrix A formed by xi, xj, xi over all ij is invertible. Yeah, because just now we have shown that if xi is linearly independent, then the matrix is invertible. So now we know that the matrix is invertible, and set of all invertible matrices is an open set in set of all matrices. That means there exists some delta such that whenever norm of A minus B is less than epsilon, sorry, is less than delta, we have B is also invertible. Yeah, this we know because set of all invertible matrices is open. Okay, so now, but what we know is from Rn to set of all matrices, I mean not set of all matrices, yeah, Rn to set of all matrices given by okay, not Rn, I mean if we define the mapping T from, okay, let's say Hn to this NNR such that the element, if you just take tuple, okay, G1, G2, Gn goes to the matrix inner product Zj, Zi, comma J, then this map is continuous, hence we get epsilon such that norm of xi minus yi is less than epsilon implies norm of a, okay, norm of t of maybe this x1 through xn minus t of y1 through yn is strictly less than delta. That means T of y1 through yn is the matrix. How we write it? Yj with yi, I over j is invertible. That means the set yi is linearly independent. Yeah, I hope this argument is clear. This is just use of openness and, yeah, I mean kind of use of the continuous mappings. Okay, let's see. Yeah, so I think this is clear. This was question number 6. Option C is okay. Now we'll go to question number 7. Let H be a Hilbert space and let En be an orthonormal equation in H. Which of the following statements are true? En converges weakly to 0. Okay, let's see. What do you mean by weak convergence? That means the En converges to 0 weakly if and only if f at En converges to 0 for all f belongs to H star. Yeah, but what we know is by Rees representation theorem, there exists y such that f at En is inner product of En with y. Yeah, I mean for every functional there exists such a y, right? So I can write now by Bessel's inequality, summation modulus of inner product of En with y is less equal norm y squared. Yeah, n going from 1 to infinity. Now that means what? This series is convergent. Yeah. So this series is convergent implies its nth term has to go to 0. So this is what we wanted. This goes to 0 for every functional f belongs to H star. So En converges 0 to weakly. Yeah, so this one is true. And okay, how about the option 2? Because see, the first option is true, so no point in checking for the second option because it says if and only if En is something, but there is no condition on En, so second is not true. Just an orthonormal sequence is enough because Bessel's inequality needs only that. En has no norm-convergent subsequence. Yeah, this is it. Okay, so let's see. Why? Because if you take any n and m, what is norm En minus Em squared? Now, because it's an orthonormal sequence, it is just norm En squared plus norm Em squared. This is just 1 plus 1, 2. That means, yeah, so you are not going to find a subsequence of En which is Cauchy itself. Yeah, and every convergent sequence is Cauchy, so you are ultimately not getting any non-convergent subsequence. So yeah, this is true. Yeah, the simple fact here we have used is every convergent sequence is Cauchy, and yeah, that's all. And norm En is 1 for all. And okay, see question number 8. H be a Hilbert space, and let En be orthonormal sequence in H. Let lambda k be a bounded sequence of real numbers. For x in H, define Ax as summation lambda k x ek. Okay, which of the following statements are true? Okay. We have to check when is Ax well defined. Yeah, well defined means when the summation converges. Okay. So if Ax is defined, summation lambda k. Okay. Hmm. Let's just consider maybe sequence of partial sum squared. You know when because we are in Hilbert space, so this is just summation modulus of lambda k squared and inner product of x with ek modulus squared onto n. But because lambda k is a bounded sequence, let's suppose bound is m, then this is less equal m times summation x with ek squared. But by Bessel's inequality, this is less equal m times norm x squared. Yeah, so that means norm ax squared is well defined less equal m times norm x squared. So a is well defined because the summation the series converges, and I mean here what we got is a is also bounded. Linearity follows easily. Yeah, you can check the linearity. Now second option says Ax well defined for which x defined only if lambda is converging to 0. This need not be true. Right now we have shown that there was no condition on lambda. It just boundedness was the only condition. So if and only if is not true. Then third one says Ax is well defined for each x and A is linear continuous. Yeah, that's true. We have just proved it. It's continuous. Linearity follows straightforward. You can check it. So it one is gone. Ninth. H be a separable Hilbert space. Okay. And En be an orthonormal basis in H. Okay. Let's see. Belongs to L2. Okay, we know. Okay. This is same as before. I mean, if you define xn as summation ck ek, then what is norm xn? Now, anyway, because xn itself belongs to the L2 now because it's just the span of EKs, a finite span of EK, where EKs are in L2, so it belongs. So I can take two norm. But this this is just summation modulus of ck squared, yeah, because EKs are orthonormal basis. And because C is in L2, this is finite. Or I can just write this is norm C. Yeah. Oh, but is that needed? Oh no, this was not needed. Okay. Okay. I need to show that it's Cauchy. Yeah. So this is modulus of CK. Can I see what this is? This is norm of summation ck ek, where k is greater or equal n, suppose. Yeah, I mean n to n plus 1 to m. Okay. Now this is summation modulus of ck squared, k going from n plus 1 to m. Yeah, okay. Now because C is in L2, this is the tail of the sequence of partial sums of CK, right? So this has to go to 0. Yeah, I mean after some point this goes to 0. That means Xn is Cauchy. So, but H is a Hilbert space, that implies Xn is Xn convergence. But as I mean the norm coming from an inner product space, it's the topology is Hausdorff topology. That means H has Hausdorff topology. I mean that's norm topology. That means every sequence which is convergent converges to at most one point. Yeah? So if we call Xe as limit as n going to infinity xn, so that will be just summation ck xk, k going from 1 to infinity. Then x is unique. Yeah, there is no need to check for any other arguments because it's Hausdorff topology. The limit will be unique. First is correct, second is correct. Third one is H isometrically isomorphic to L2. Okay. So isometrically isomorphic means we have to give an image, we have to give a mapping. So what I'm defining is any element, any sequence. Suppose I define a sequence as, I mean, maybe just same ck if I take sequence. This will map to summation ck ek. So right now we have showed this is well defined. This is an element in L2. No problem for well definedness. And what is norm of phi of ck? This is same as norm ck. Yeah, I mean instead of saying ck, okay, I think I'll just say c, where c is ck. So this is phi is isometry. This is easy to verify. Yeah, and for any y belongs to H, because En is an orthonormal basis, you can write y as summation inner product of y with En, then phi of this sequence is equals to y, whereas this En will belongs to L2. Yeah, this follows from the Basels. Oh, no, Parseval's actually. Basels is just, I mean, from Basels also it follows. So the isometry follows from Parseval's. So question number 9 is clear. H is isometrically isomorphic to L2. Okay, so this question number 10 I'll leave you for an exercise, but I can just give you some hints. Maybe this is okay. What this says is x to n fx is 0 for all n. That means essentially integral 0 to pi px dx fx will be 0 for all polynomial p. P. And if you take any f belongs to c 0 pi, there exists sequence of polynomials which converges to f. That means integral Pn f converges to integral f squared, yeah, which is just norm f, 2 norm. Yeah. But this is 0 for all n. That means f is 0. So this one follows. And in similar way, you can do this one also. No, this is wrong. Second one. I mean, if you take f equals to constant 1, then still integral 0 to pi cos nx 0, but this is f is not identical 0. And this is correct, you can verify. Yeah, so this is assignment 10. I hope everything is clear. Okay, so if you have any doubts, you can ask or see you in the next session.